Good morning, welcome. So we are discussing the Burgers equation, and we have been focusing on the inviscid Burgers equation. There we have been studying so-called Riemann problem when we have a discontinuous initial condition. So we saw when the left state is larger than the right state, we get a shock. So that is the situation when we have 0, when we have u, when we have x, when we have the ul larger than the uy. Then we will have a shock wave, and that will then move to the right. So we will have them after some time t, we will have this continuity will have moved with a shock speed s. And then the solution will be that we have so that's what we have here, that is the initial condition, and after a while, after time t, then we will have this shock solution. So that will be the solution, say, at the time t. We also saw the other way, that is when we have a rarefaction wave, when the ul is smaller than the ur. And then we have the following situation, this is just the other way around. We have u. And now the u left lower than the u right. And what then happens is not that we get a shock, that would be an expansion shock violating the Lux entropy condition, but what we get is we get a rarefaction wave, because this will move faster, so after a while this point will be, say, here, and this point will be, say, here. So then we will have something like that. So in the solution after that time then will be, again, this is what we have here is the initial condition, u of x is 0, but what we get after time t, that will be then this rarefaction wave, so this is the solution here. So that would be then the solution u of xt. That would have traveled here, the distance would be here the ult from 0 there, and the distance here would be urt. And we argued that if we would assume that we had a shock here, it would violate the Lux entropy condition. And that says the following, that was 19. The general formulation is that the f prime, that is our flux function, at u left must be larger than the shock speed and larger than the characteristic speed on the right. And the thing that we can check that, the f prime for the inviscid Burgers equation is u. So the ul is then on the left, that is clearly larger than s, because we found for the shock speed that was ul plus ur half. That was the shock speed. So that is okay. And also the shock speed is then also larger than f prime of ur, which is ur. So that is okay. But we saw it is not okay if we would assume an expansion shock. The thing that I forgot to tell you is that this Lux entropy condition is valid for convex fluxes. So that you can add, so for convex fluxes, for convex flux functions. And that is f of u, and that means that the second derivative of f with respect to u must be larger than 0. So that is the thing that I just want to add here. In our case, we have the inviscid Burgers equation. The f is u squared half. First derivative is the characteristic speed, which is u, and the second derivative is 1. So clearly we have a convex flux function for the inviscid Burgers equation. So we can have, of course, much more complex initial conditions, and we saw examples with the cosine, different forms of that, how that would behave. And the question is now, when we know about the mathematical and the physical classification of the inviscid Burgers equation, how can we discretize it? So that will be the topic that we are looking at today. We do it again in a more general form, not just looking only at the inviscid Burgers equation, but more general. And so for conservation laws. And that will bring us to the chapter 2 after the mathematical and physical classification, and that is then entitled as the conservative or the conservation form of finite difference methods to do the discretization of conservation laws. So why is that important? Well, we could try a non-conservative form, and we will see that what the problem is with that. Let's first try a non-conservative form. We look at the non-conservative explicit finite volume method. That was the one that Bernhard showed you on Tuesday. And that would then be again for the inviscid Burgers equation. And that was, we have different forms for that. And now we would take the form 2. The form 2 was what we already classified from the mathematical point of view as the non-conservative form. That was, if I write it now with indices, ut plus ux equal to 0. So if we would do a discretization on that, we could easily know, we can easily find out what will be the upwind method, because when we know u, it is similar to the c in the linear advection equation. So when we are at a grid point xj, we know uj, and that can tell us from where the wind is blowing. So let us then take this idea, and then we would have, call it 20a, the time discretization as usual, the ujn plus 1 minus the ujn divided by delta t. And if the uj is now positive, we will take then the discretization from the left, from where the wind is coming. And that would be then the upwind form, that would be then the ujn minus the uj minus 1, would be a backward difference. And that is then 0, and that would be the case if the ujn is positive. So then we have a clear discretization, and that was what Bernhard used for some of his demos on Tuesday. If we have, however, uj negative, we have to take the discretization of the du dx from the right. Then the wind is blowing from the right. So that would be then the other option. We would then have again the same time discretization, uj n plus 1 minus ujn divided by delta t. And now if the ujn is negative, we take here the uj plus 1 n minus ujn divided by delta x, and that is equal to 0. So that is then the case if the ujn is negative. And that is reminding you of exercise that you did for the linear advection equation, when the C, the advection speed, was negative. Then you used this similar discretization. Well, let's see what we can get with that. So we look at the code that you got from Radar. With burgers, where we have a menu, and here comes up a menu. So we choose now the discretization with non-conservative output method. So let's see, that was the burgers. So we have the choice, we choose the inviscid burgers equation, we choose now the upwind non-conservative, and we choose a piecewise constant initial condition. It's actually starting from the left, so that should give us a shock. We choose 101 grid points, and we choose a time step like this. So then we get this solution here. So let us turn it to see what it is doing. Well, it is just standing still. It is on the left where we have it started. So we have here the x and we have here the 0. So here is it started with 1 at the left boundary, and here is a time. So it doesn't move. So this is wrong. We should have a shock moving into the domain, but it doesn't move. Can we understand why? Well, yes. U is positive, so we from at the boundary. So, and if we start this equation, we will start it at say if j equal to 0, let's say that would be then our boundary condition. That is 1, but everything else is 0. So if we start at j equal to 1, this will be 0. So then this all will be 0, and we will just get u1 at the new time level minus u1 at the old is equal to 0. So that means nothing will change. So we will get simply an unchanged solution, which is wrong. And that is due to the non-conservative form. If we would apply it to other test cases, we would also observe that we get the wrong shock speed. Here the shock speed what we get from this is 0, completely wrong. We should get 1/2, because we have 1 on the left, we have 0 on the right. The shock speed, as we discussed before, is the average, arithmetic average, should be 1/2. So that is wrong. So that is the problem with the non-conservative form. We don't get the shock speed right. And if we would apply it to other problems, we would see we cannot conserve properties with that. So let us try then the conservative form instead, and try that one. So now we go again through the same menu, choose the Burgers equation, but now we choose the upwind conservative method. We choose again the piecewise constant initial condition. We choose again 101 points and 0.005 as time step. Now we get something. Let's look at that. So, yeah. So now we can see here really a shock. It is of course not really completely sharp, but relatively sharp. Here we have x, here we have t, so the shock has been moving in. And if we turn it a little bit, then from the back, we see it has come close to or around 1. And that's what it should be, because it has traveled a time 2 with a shock speed of 1/2. 2 times 1/2 is 1. So then it is roughly where it should be. So that means the conservative discretization gives us what we expect, and the shock speed is okay, but the non-conservative does not. So that is the argument why we shall not use non-conservative form, but a conservative form. So then we have to find out what that is, but first we want to write down the general form. Yes?
Hadde du gjort på en måte brukt en annen altså en annen diffligning og på en måte fått den i gang, et annet diffligningsskjema?
Well, if you had tried to get it started, you would have the same problem at another point.
Okay.
So imagine you had that at a point, say in the middle. Then in the middle, at some point, you would then be at the boundary again of the discontinuity. So you would have then, if we have here x, we have 0, we have 1. Say we would put the initial condition or u of x0 not at the left boundary, but we would put it in the middle. If you then are at the point here, where the say we are here, say we are here at this point, we could choose it at this 1, but if we are here at a point, say xj, where the solution is 0, you will have exactly the same problem. So it will not help. So it is fundamentally flawed to use this approach, because we lose the conservation property. That is another point. The conservation property that we will see is that essentially the fluxes that, or the changes in the solution, if you imagine that for the whole domain, it should be governed essentially what is getting in at the left and at the right boundary. But here with this formulation we cannot achieve that, because when we do the discretization, the contributions that we have at each we call it later on phase, will not cancel. We'll see that now when we look at the conservative form. Sorry?
Vad är det som är bra med den icke-konservativa då?
What is good with this non-conservative form, it is easy.
Okay.
Because you know directly writing it down how you should do the discretization. You know exactly, put the finger in the air, U is positive, take this, U is negative, take this. So that is easy. So that's the advantage. If you have a non-conservative problem, then you can use it. But if we have a conservative problem, that we have in our case, we should use that. Because there we have this property that I'll explain you in a minute, in addition to getting the right shock speed. So we can conclude from what we saw that so the non-conservative form that we saw, non-conservative, we just call it FDM 20, does not yield correct shock speed. And it does not fulfill the conservation property. And that is following. Does not conserve that clear in a minute, because what we would like to have is something that comes from the equation that we originally had to derive the conservation law, and that is the integral form. So we cannot integrate this already the non-conservative form of the differential equation, that it's not possible. So the conservation property that would mean when we have a discretization over an interval x, and we have here our left boundary xa, right boundary xb. So here we have u. Then we will have a couple of grid points. Then we do the discretization on that. And in the end, we should have that when we integrate the equation, say du dt dx, we saw what we should get then is that we have the flux that is on the left, u on the right, ux minus the flux function on the left, uxat. That should be 0. And when we would do the discretization on all the intervals that we have here, and we sum them, in the end we should get that. So that is a criterion. With a non-conservative form we cannot get it, because then the contributions that when we apply this idea to each of the subintervals here, it will not work. So instead now we want then to have a conservation form of the discrete equation, and that we can express them in the following form. A finite difference method in conservation form. So then it should mimic this property for each cell. And what we shall do now, we shall imagine that similar to this idea here, that we have now the situation when we pick out a few grid points, just a few grid points. Let's see, we pick, say, grid point xj, grid point xj plus 1, and the grid point xj minus 1, just to zoom in, so to speak. So what we want to do now, we want to essentially define a cell for this grid point by the midpoints. And we call these midpoints, to be that also really from the for the heat equation, xj plus 1/2 and xj minus 1/2. So then we will have an interval that is defined by the midpoints. So it will be, and this will be our interval that we consider. And then we want to formulate things in such a way that we get the conservation property from the differential equation, now not from the end, from the start to the end, but from the start to the end of this small interval, this small cell. And if we want to achieve that, we do the formulation in such a way that we write now the ujn plus 1, the time derivative. So there we have some freedom. Here we choose now the explicit Euler for the illustration. But that we choose now the flux functions at these midpoints. So we choose now the flux function here at the midpoint xj plus 1/2, and we choose the flux function here. Then we take the difference of that. Remember, what we are discretizing is here for the conservation law, that is ut plus f of ux is equal to 0. That is now the general discussion for the conservation law. So we do now the discretization of this flux function by taking it at the midpoint to the right minus the midpoint to the left. And we call then this flux function by this symbol f. So that will be the fj plus 1/2 minus the flux function j minus 1/2 divided by delta x equal to 0. So these flux functions are supposed then to approximate the correct flux function at the midpoints. And if we do this, imagine this, and we sum over all the discretizations that we do, then we will end up that we get only what is then left. We do this idea here, we would then, if we, let's see, here I have, it looks like, we would choose the grid points like that. That would be our grid points. So at the boundaries we have to do some special thing then. But if we would do that, then the contributions that we have from, say, we have the flux, let's see, this is J, and here we have J plus 1, here we have J minus 1, so these are the grid points, the x's. Then the flux that we have here, the, say this would be now the F, we change this now to F. We have here then the Fj plus 1/2. That would be the Fj plus 1/2 for the cell J. But it would be the same flux that is entering the cell at J plus 1. So this flux that we have here, that is located here. Here it comes with a positive sign. In the right neighbor, it comes with a negative sign. It is the same one. Imagine we go one, we take J plus 1 here. Then it will be exactly the same. So the flux that is leaving the cell J is entering the cell J plus 1. So if we would just write them down, they would exactly cancel. It is like an integral. One is, you take it as going out, you take it positive, the other is going in, you take it negative. The sum is 0. And in the end, we will just get what is coming in and what is getting out. So then we will get this property here, the conservation property. So that here first, coming back to this, that is called in the first place conservation form. If we want to have a scheme, it should be in such a form, because then we can guarantee that the conservation is satisfied. So let's make that clear. So we have to note what the f was, because it is, we are now introducing the f here, the little f. The little f, j plus or minus 1/2, is called the numerical flux function. And that depends then, determines the numerical method that we use. And in that case, it is defined at xj plus or minus 1/2, which we identified as the midpoints. And if we look at the conservation property, now not for the whole interval, but just for the cell that we discussed, for this cell here, then we get the following. So this form, the finite difference method conservation form, that mimics, we can say, that mimics the conservation law in integral form. That was, the integral form was 8. And now if we do that then in the following form, now 20. now we consider then, we can say for the interval xj minus 1/2, xj plus 1/2. So it is now for this interval. For the interval that we have here identified for the grid point xj. For that we can do now the conservation board, and then we will have the integral from xj minus 1/2 to xj plus 1/2 of du of xt dt, the time derivative, integrated over this cell. This we call either control volume or cell. And then we will have f. Let's see, if we have the flux, then it will be our capital F. It will be our capital F, that will be then of u, and that will be of xj plus 1/2 t. So that is then, we apply now what we have here for the complete domain to just this cell. Then we have here f of u of xj minus 1/2 t. And that is then supposed to be 0. That is our conservation. And if you now look at this a little bit more carefully, you will see that when we approximate this here by the midpoint rule, so that we take it, the value here at the grid point xj, and we use the explicit Euler method, then we can approximate this here by ujn plus 1 minus ujn divided by delta t. We are not yet ready, so this is a discretization of that. And now we assume that we have a grid spacing of delta x, so we have to multiply it by delta x. So then we have a discretization of this. And if we approximate this here by the flux function fj plus 1/2 at the time L, that's a possibility we can do if we use explicit Euler method on the whole thing. We assume that we approximate the correct flux function by the numerical flux function at this point. We have that. Minus the same here. We have the numerical flux function at j minus 1/2. If we look at this now, and we compare it with the conservation form, we will see they are identical. We have just to divide by delta x to get this form. So that means when we use the conservation form, we are essentially using a discretization of the integral equation. And then we are discretizing really the conservation form that will us allow to get this property of conservation, what we discussed at the beginning. When we sum up this for all our cells, we will in the end get the change of our conserved variable in the whole domain is governed by the flux that is going out at the right boundary minus the flux that is coming in from the left boundary. And then we have the conservation in place. And what we are discussing here is actually the finite volume method. So then when we use this idea in our finite difference method in this form, we are essentially using, you could say, the finite volume method. So then, just to finish up on this discussion to the right, on 22, so with the uj in the discretization that we discussed for the integral form is considered as cell average in the cell or control volume xj minus 1/2, xj plus 1/2. So that was what we just had before. And that would be the following, 23, that we consider uj of t is approximating an average is the following. It is the integral over the cell xj minus 1/2 to xj plus 1/2. And we are integrating the exact solution to our problem u of xt. So then we get an average by dividing this integral by the delta x, which is the difference. So what we do here, we have x, we have xj minus 1/2 and xj plus 1/2, and we have the grid point xj in the middle. So then we have u of xt, for example, we have some form of it. We don't know exactly, but what we are interested here is just the average. So we integrate over that, we divide, the spacing here is the delta x, then we get the cell average. So if uj that we are discussing here is considered as the cell average, in this what we came up here, then the discretization that we have here, which is equivalent to this, corresponds to the finite volume method. So then 21, which is equivalent to the form we derived from the integral form, corresponds to, if we are to be precise, explicit finite volume method. So then we have already some clue on this method. We touched on it in the beginning when we looked at an overview of the different discretization methods. But what we are discussing here is the finite difference method. In the finite difference method, we do not assume that we have cell averages, but we assume that we have values at grid points. We have nodes values at the grid points that we want to approximate. So that's the difference. So, but in finite difference methods considered here, we approximate, or uj of t that we consider is approximating the exact solution at the grid point at some time t. So that's the difference. Here we are approximating point values. And in the finite volume method, we are approximating averages. So that means point value is approximate, not an average. So now we have given some motivation why we would use this conservation form. We give a conservation property, and what we can also note from this form is when we use then the explicit upwind method that we shall derive later, we shall see that we can get the correct shock speed with that. So that is then okay. But let us continue on this form now. How do we get these numerical flux functions? So what we observe is, or what we can imagine is, just by thinking about it, we would like to have these flux functions. For example, if we are at a grip, we have here at xj, we have here xj plus 1. We would like them to depend on the values that we have at xj and xj plus 1, for example, if we want to have the flux at j plus 1/2. So that means we want to have them local. And that is also what we usually use. So the numerical flux function usually, and also on other one, depends on next neighbors. And the next neighbors are, for the flux function, fj plus 1/2, uj and uj plus 1. So that means we write that now in this form as a function of uj and uj plus 1. So that is what we shall usually observe. We cannot take more, we can do that, but this is the most common situation. What is our requirement? Our requirement will be that we saw from the integral derivation that these flux functions should approximate the correct the correct flux function f, capital F. So that is the requirement. And that is what we then require for consistency. So that means when we plug in u for uj and uj plus 1 in our flux function, so that we have the same values on the left and the right, the flux function should give us the numerical flux function should give us the correct flux function with this argument. So we should get f of u. Remember, the f of u was the one that we have in the conservation law, the ut plus f of ux equal to 0. So it is this here. In our case, that is the u squared half. So it means when we plug in our numerical flux, the same value, u, on both sides at xj and xj plus 1, we should get the correct flux function. Okay, so then we can summarize, and as we shall see in a minute, that the conservation form, this form here, then is actually derived from the conservation property. So that is then satisfied by this form, and we get the correct shock speed. So the conservation form, that is 21, guarantees conservation property and it guarantees the convergence of a shock solution with correct shock speed. So that is the reason why we are using this conservation form. So we get this conservation property. So we would sum that over all our grid points. We will just get the change in the whole domain governed by the fluxes to the right of the domain minus to the left. And we get the correct shock speed. So let us just look at this. This is substantiated by, we have already seen this example, yeah. So just that was then the example that we saw here from the Burger's program. Okay. So that is the background, and that allows us then a couple of possibilities to get numerical methods in conservation form, and we shall discuss the explicit upwind finite volume method in detail after the break. Let's see, today we have Friday, so then the break is only 10 minutes to allow the people from Tühol to get back in time.